So today is a great pleasure to welcome our speaker today, who's Professor George Fuller, who's the Distinguished Professor of Physics at the University of California in San Diego. Briefly, George grew up in Los Angeles, or near Los Angeles. He went on to do an undergraduate degree at Caltech, which is also near Los Angeles. And then he got a PhD at Caltech, again, near Los Angeles. He did his PhD with Willie Fowler, the Nobel laureate, who's one of the founders of nuclear astrophysics. After his PhD, George briefly came to the Midwest and worked in Chicago, and then he went back to the West Coast where he worked Santa Cruz, University of Washington, and Lawrence Livermore National Laboratories. He then transferred down the coast to the University of California, San Diego, where he's been ever since. He's won a whole host of awards. I just want to specifically mention that he won the Hans Bethe Prize from the APS. That's an award for excellence in nuclear astrophysics, which makes sense since George is one of the leading nuclear astrophysicists of his generation, and we're very happy to have him here today. He's made a lot of important contributions, including contributions to our understanding of Big Bang nucleosynthesis and the way in which supernovas explode. In both of these contexts, neutrinos are a super important part of the story, and they're also very difficult and subtle to deal with. So today, he's going to tell us how that works. He's going to tell us about the insidious neutrinos, entropy, and gravitational collapse.
Thank you, Fred, for that nice introduction. And thank you, Keith. And thank you very much for this honor inviting me to give this lecture. This morning I've been talking to a number of scientists here, physicists and astronomers here at University of Michigan. I'm impressed that there's so much happening, there's so many really exciting things going on, and basically what I've discovered is that all the things that are exciting to me that I'm talking about here are many of the experts are here at the University of Michigan. So I hope I can inspire a little more enthusiasm also in that regard. So my opening slide here has a picture of a galaxy, and you may see it here, there are two core collapse supernovae that happen in this galaxy a few years apart. So a question I'll ask, and in all seriousness, is do we even know the fundamental physics necessary to understand the evolution of stars and compact objects now? What worries me is if you think about the history of the subject, in the 20th century, I can think broadly there were three key developments in understanding stellar interiors and the evolution of stars. One, of course, is just quantum mechanics, especially the connection between spin and statistics. The other was the development of nuclear and particle physics. Laboratory experiments went hand in hand with astrophysical modeling. My roots are in Kellogg Lab at Caltech, but many universities engaged in trying to find and measure nuclear reaction cross-sections that were important in astrophysics, and in turn, astrophysics fed back on the targets for the laboratory. And the third thing, of course, is the development of large-scale numerical simulations. But if I think today, we already know that the otherwise very successful standard model is inadequate. Can't explain dark matter, dark energy. There are aspects of neutrino physics which are very mysterious, some of which I'll mention. And so it kind of begs questions that, again, I talked to folks this morning about, and they're experts here in Michigan. Are there secret interactions between neutrinos? As I said, we don't really know a lot about neutrinos. Are there new light particles that figure in the physics of stars? Are there whole new dark sectors of particle physics, elementary particle physics, kind of like the standard model, but different? The advent of multi-messenger astrophysics, and especially gravitational wave astronomy, is already a game changer in this regard. This last summer, we had a meeting at the Institute for Nuclear Theory in Seattle, the title of which was Dark Matter and Compact Objects, Stars and Low Energy Experiments. There's this ferment right now, this revolution in ideas about new light particles and new particles and what that might mean for modeling compact objects. So let me remind you that physicists like to gauge the strength of interactions in terms of a cross-section. It's a ratio of the event rate that's measured in a lab divided by the flux of projectile particles on a target. That's called the cross-section. And if we look at the strong interaction, it's huge. It's basically the area of the particle, which can be very large. If you think about the de Broglie wavelength of a particle that has low momentum. the gold standard here is the Thomson cross-section for the way photons scatter on electrons. That cross-section is about 10 to the minus 24 square centimeters. Call that a barn, kind of in the colloquial, kind of is in the broad side of a barn. The weak interaction, which is the subject of a lot of this talk, is some 20 orders of magnitude weaker than electricity and magnetism. In gravitation, don't even think about it. It's ridiculously small. Okay? So the weak nuclear force, much about this aspect of nature remains mysterious. And it's a subject of a lot of intense work in the lab and also theoretically. But despite this label of weak, which it certainly deserves, as I just showed you, I claim it's the basis for all of humanity's energy sources in the end, right? Obviously fossil fuels that were fossilized sunlight in a way, clearly solar, nuclear fission and fusion. Fission comes from, say, uranium, and as we'll see, that's intimately bound up with what happens with weak interactions. And of course, fusion of deuterium and tritium, those things probably arise largely in the Big Bang, or at least deuterium does. So the only one I can think of that's not is tidal energy, but maybe I'm wrong about that too. So, and what I'm going to tell you is that there's an insidious conspiracy between the weak force and an even weaker force, as I showed you, gravitation, that sets the conditions in the early universe, murders massive stars by causing their collapse and explosion, but brings about the creation of the elements in both of these areas. Okay. So let me remind you, here's the zoo of elementary particles in the Standard Model. 3 elementary particle families. Each family has 2 quarks. Each family has a charged lepton. The first family you're probably quite familiar with. That charged lepton is the electron. The muon and tau are kind of heavier versions of that. Each family has a neutrino. All these families, these particles are spin 1/2, except for the force carriers. They're fermions, in other words. They all have electric charges except for the neutrinos. So neutrinos are like the charged leptons and quarks. They're spin 1/2, but unlike them, they have no electric charge, which makes how they acquire mass a little funny in the Standard Model. Each particle on this chart has its own antiparticle, of course. So there are 6 kinds of known neutrinos: electron flavor neutrinos, and electron antineutrinos, etc., for the mu and tau neutrinos. Okay? And so those labels of flavor determine how the neutrino interacts with matter. Hans Bethe figured out how stars shine, at least how they shine for a long time, and it's the weak interaction. So the key reaction that happens in stars like the sun is proton plus proton makes a deuteron. A deuteron is a bound state of a proton and a neutron. And you produce a positron and an electron antineutrino. Electron neutrino, sorry, that one's wrong. I don't know why I get that wrong. And you can see Hans has it right, actually. You can see it on the blackboard behind you, okay? An electron neutrino is produced. And we detect these neutrinos in the laboratory now in big neutrino detectors. The point is that if you're going to burn hydrogen, fuse 4 protons into a helium nucleus, the helium nucleus has 2 neutrons. So it's only the weak interaction that can intervene to turn those protons into neutrons. Okay? So here's a picture of the sun in X-rays, photons. Here's a picture of the sun in neutrinos. Of course, the pictures are kind of fixed up, so the same angular scale, but the angular resolution of the SuperChem Canada detector is not very good. If it were, there'd be a bright spot at the center of the sun that produced the neutrinos, right? Because the nuclear reactions are extremely temperature sensitive, so they're really coming from the center of the sun. Okay, so neutrinos are nice as diagnostics of what powers stars like the sun, but neutrinos are murder weapons when it comes to massive stars. So here's the famous quote from T.S. Eliot. You can read about neutrinos there. Oh, dark, dark, they all go into the dark. The vacant interstellar spaces, the vacant into the vacant. So it's really these ghost-like neutrinos that fly right through huge amounts of matter, like all the sun, without being absorbed, plus the nonlinearity of gravitation that brings them down. To see that, we have to have a little bit of an aside on stars and on entropy, to think a little bit physically about entropy. So self-gravitating systems like stars or star clusters in many cases, they have negative heat capacity, right? Heat capacity is the heat flows out, what happens to the temperature? For stars, or self-gravitating systems, they can shrink in their gravitational potential well and actually heat up. So I like to say when they cool off, they heat up. And Yogi Berra did not say that, although it sounds like he did, okay? They get into trouble, though, when the source of their support pressure, support against gravitation, is coming from particles, either elementary particles or nuclei or electrons or stars in the case of clusters. Whenever those things that are supplying the pressure, quote unquote, are moving near the speed of light. To see this, let's look at the balancing of forces in a star, so-called hydrostatic equilibrium. If I take a little fluid element in the star, add up all the pressure forces on it, and then set that equal to the gravitational force on that fluid element, then the forces are all in balance. And from that, we can get the famous equation that the astrophysicists solved, the equations of hydrostatic equilibrium. But having an equilibrium of forces does not guarantee a stable equilibrium. It just says the pressure force is balanced. It doesn't say whether there are restoring forces or not. Nor does it say whether it's thermally stable. In fact, for that, we would need a positive entropy gradient. Otherwise, we get convection. And for most of the big stars I'm going to talk about here, they're actually convectively unstable. Nor does it guarantee chemical equilibrium. And in fact, the evolution of stars from a nuclear physics perspective is an evolution towards establishing nuclear statistical equilibrium. Okay? That's sometimes lost in the hustle and bustle of the myriad of nuclear reactions that happen in big stars. So one way, and a very important ingredient in determining stability, is the so-called adiabatic index. So let me walk through what this means physically. Gamma 1, d log pressure, d log density at constant entropy. So physically, think of it this way. Cup your hands around a piece of the stellar material. This might hurt. Squeeze it quickly to a higher density and ask how much does it push back. But do it quick so the heat doesn't flow. That's what that means, that the entropy is constant. Okay? So it's, in a sense, it's kind of the spring constant of the material. Now, if we have a gas of Maxwell-Boltzmann kind of particles, the particles moving much less than the speed of light, like the gas of air molecules in this room, then this adiabatic index is 5/3. On the other hand, if we had a gas of photons or other particles moving at the speed of light, the adiabatic index would be 4/3. If we ask, how do we guarantee that a star is stable? The answer is that the pressure average value of that adiabatic index needs to be greater than 4/3. Now, that's in Newtonian gravitation. General relativity is a different story. Remember, the essentially new feature of general relativity relative to Newtonian gravitation is nonlinearity. So a bit of space-time curvature makes a little bit more space-time curvature. So this is exactly why the orbit of Mercury is not a nice ellipse. In fact, the potential is not 1 over distance. It's a little bit steeper than that, right? As Mercury gets closer to the sun, the force of gravitation is a little bit stronger than Newton would have predicted. And so the net result is the perihelion precesses, right? The major axis of the ellipse precesses. And that's a tiny effect, but measurable. Likewise, now, take this material in the star, push the star inward a little bit. The pressure forces balance gravity. If they do that, if we're at gamma 1 of 4/3, but gravitation grows a little bit faster than it would in the Newtonian case, and so it could be unstable. Now, this term, that it has to be greater than 4/3, plus this tiny term, that's of order the Schwarzschild radius of the star divided by some length scale, some radius in the star. If I look at a white dwarf, for example, then that correction is tiny. It's about 1 part in 10 to the 4. So that would make no difference in the run of pressure or density in the star, but it's absolutely the thing that determines stability in these stars that are supported by particles moving near the speed of light. So you can kind of see this with an analogy of a ball rolling on a surface, so that with Newtonian gravitation and Maxwell-Boltzmann-like physics for the gas particles. Pressure average value greater than 4/3 is like a ball rolling in the bottom of a well. Included there are restoring forces if you perturb the position of the ball. If I have Newtonian gravitation and just pure radiation, then it's like a ball on a flat surface. Costs no energy to move that ball around. Likewise, a star supported by radiation and Newtonian gravitation costs no energy to move it in or out. Put in general relativity, that tiny extra nonlinear piece, and it becomes unstable. There are no restoring forces. This is called the Feynman-Chandrasekhar instability, after these two characters, and there's an interesting history of this instability. Chandra wrote a paper on it, of course. Feynman never did. It was you can read Kip Thorne's introduction to Feynman's lecture notes, where essentially this is kind of essentially an exam problem. Okay, so whenever the pressure support for a star comes from particles moving near the speed of light, the star is quote unquote trembling on the verge of instability. I heard that from my mentor, Willie Fowler. So if we look at the fate of stars in various kinds, here's mass of the progenitor star. Here's the entropy per baryon on the main sequence where it's burning hydrogen. We'll talk about that in a minute. Here's the entropy per baryon when it goes unstable. Here's a core mass if it has any. Here's what kills it. And in each case, it's where the adiabatic index is close to 4/3 and general relativity shoves it over the edge, and or internal physics shoves it over the edge. And here's the fraction of the mass of the collapsing core that is radiated as neutrinos. Of the rest mass, it's huge. So let me talk about these stars in the 10 to 100 solar mass range. These are the stars that progenitors give rise to what we typically call core collapse supernovae. And yes, 10% of the rest mass of the collapsing core gets converted into neutrinos. So here's the evolution of a 25 solar mass star, roughly the progenitor of the 1987A supernova. Here's a Scientific American article by Tom Weaver and Stan Woosley. This is an excellent article. And you can see that this thing evolves. It burns on the main sequence. There's the main sequence, just like the sun does. But unlike the sun, it burns up its hydrogen in something like 10 million years, whereas the sun takes 10 billion years, 1,000 times longer, to do that. And it evolves away from that to higher burning stages and eventually collapses. So let me say something about entropy. So entropy is Boltzmann's constant. You've all taken statistical mechanics or thermodynamics, and if you haven't, you will. Entropy is Boltzmann's constant times the log of the number of many-body states in equilibrium, or essentially the number of ways you can arrange the matter in equilibrium. Okay? And I know this is true because it's on Boltzmann's tomb, as you can see here. Okay? So the way to think of this in nuclear physics is as follows. If I have 6 red neutrons and 6 red protons, and they're running helter-skelter, each with 3 translational degrees of freedom, that's kind of a high entropy configuration, right? Because there are 12 times 3 degrees of freedom or 36 translational degrees of freedom. If, on the other hand, I stick all those 6 nucleons into a carbon-12 nucleus, and the temperature is low enough I'm not exciting carbon-12 internally, then I just have 3 translational degrees of freedom. So you can see here that higher entropy favors lots of free particles. Lower entropy favors putting the nucleons in to force them to move around as a unit in a big nucleus. Okay? That's the way to think about entropy in a nuclear physics context. So now let's look at the burning stages of this 25 solar mass star. So like the sun, it burns hydrogen on this main sequence, again fusing 4 protons into a helium-4 nucleus. This is a big star, so it doesn't do it by that proton plus proton deuterium plus positron plus electron neutrino route. It has other weak interactions whereby it, the CNO cycle in particular, whereby it converts protons into neutrons. It's a bit hotter than the sun. Of course, it's heavier, so it has to have higher pressure to hold it up against gravitation. So the sun is about 1 keV in temperature. This is 5. It's less dense than the sun. The sun is about 100 grams per cubic centimeter in the middle. And sure enough, it burns hydrogen much more quickly. Makes sense, because the nuclear reactions are all very temperature sensitive. Burns hydrogen to helium. The helium We burn. We have to get to higher density because it burns by 3 particles coming together at once, 3 alpha particles. But you can see that takes, around 500,000 years, okay? And then the helium burns the carbon and oxygen, neon, silicon, eventually the silicon sometimes will burn to iron, or iron peak elements. And you can see that there's this fantastic decrease in the time it takes to burn the ashes of the last stage, from core carbon oxygen burning onward. Why is that? It's because massive stars are giant refrigerators. Okay, this is the negative heat capacity thing. So from core carbon oxygen burning onward, the neutrino luminosity exceeds the photon luminosity. So this star is struggling like crazy to burn stuff to get energy out of fusion. And by the way, past hydrogen burning, it isn't very efficient. Hydrogen burning, it gets of order, 1% of the rest mass of the reactants out. If you're burning heavier things into even heavier things, it's more like 1/10% of the rest mass. So it's just not very efficient. And moreover, all that energy is getting dumped into neutrinos, which just escape. Okay? Nevertheless, the temperature is going up, so that finally, it's a temperature that's of order 1,000,000 electron volts, or 10 to the 10 kelvins. Okay? Nevertheless, it really is a giant refrigerator, because the entropy per baryon that was about 10 on the main sequence, that's like the sun, winds up at about 1. This is the entropy per baryon in units of Boltzmann's constant, about 1. And so you might say, well, but the temperature is really high. But the density is higher, and the entropy is low. So by any standards, that's extremely well ordered. So in some models, for example, of the equation of state, the Coulomb energy between the ions is larger than kT. And so the collapsing core of a supernova can be at a temperature of 10 to the 10 Kelvin, but essentially a frozen crystalline solid. Weird. And so that core, I'll put in quotes iron, because it need not be iron. Sometimes you've heard that stars collapse when they burned iron and you can no longer get energy out of fusion. That's not true. Okay? Some of these stars will actually, the lighter ones, will collapse during when they have an oxygen and neon magnesium core. Okay, so the core is about the size of the Earth. It's got about the mass of the sun, a little bit, 40% more than the mass of the sun. And of course, it's supported by electrons. You took all the electrons and you shoved them into this tiny volume. And by the Pauli principle, they got shoved up into very high momentum states, high energy states, so they're moving near the speed of light. So this thing is trembling on the verge of instability. Electron capture or some readjustments in the nuclear statistical equilibrium can shove it over the edge. Once it goes unstable, it will, in about 1 second, collapse to the point where the nucleons touch. And that's like hitting a brick wall. Suddenly, gamma 1 is 5/3, can't shove the nucleons into each other, there's a shock wave that's generated. Actually, the initial radius is about 40 kilometers, but within about 1 second, it shrinks down to about 10 kilometers, about 6 miles. So that's pretty dramatic. So we can look at that. The entropy per baryon as it collapses is very low. The Fermi energy, the highest energy electrons at the top of the Fermi sea, have energies that are like 40 or 50 MeV. The temperature is still substantial, but much lower. And the baryons are for the most part, in very heavy nuclei, as you might expect with the entropy that low. So the neutrinos dominate the energetics of all of this. So think about it. If something of the size of the Earth and the mass of the sun collapses down to something that's, the size of Ann Arbor, that's a lot of gravitational energy release. Pretty much 99% of that goes into feeding the neutrinos and the neutrino fields. So the explosion, if there is one, the astronomers will tell you, they add up the optical and kinetic energies, about 1% of the neutrino energy, about 10 to the 51 ergs. Total neutrino energy is 100 times larger, 10 to the 53 ergs, and that's 10% of the rest mass of the star. That's just the gravitational binding energy. The neutrinos that are trapped inside, eventually, as the star collapses, the density is so high that even the weak interaction is good enough to trap the neutrinos. and they'll diffuse out to the edge of the neutron star and then freely stream. Where edge of the neutron star is a little bit of a fuzzy concept, no pun intended, but nevertheless, this is roughly what happens. And that time to random walk for a neutrino to random walk to the surface there is of order of seconds. There's kind of equipartition of energy among all the neutrinos, so luminosity in each of those 6 neutrinos is about a few times 10 to the 51 ergs per second. So sometimes we can get an explosion out of this. But again, the explosion energy is really very low. Only 1% of the energy that's resident in the fields of neutrinos. So that if you're into modeling how supernova explosions work, your job is to figure out how to couple 1% of that neutrino energy into kinetic energy or heat to re-energize the shock wave that's formed when the star hits bottom at nuclear density. Here's a slide from Tony Mesa Kappa. It's a great slide. It shows you the protoneutron star. You'll see that these reactions in the material outside the neutron star, mostly the neutrinos just freely stream through, but once in a while a neutrino, a nu E, will capture on a neutron to make a proton, or an electron antineutrino on a proton to make a neutron, and that'll dump a little heat. Okay? And motion, hydrodynamic motion or convective motion of the material either inside the neutron star or below the shock can aid that. And so, we can get an explosion that way. So let's think about the material that's moving away from an explosion like that. And here I have a cartoon that summarizes Big Bang nucleosynthesis on the left and the kind of nucleosynthesis that might be different, that we might get from the neutrino-heated material moving away from the neutron star on the right. Okay? So for Big Bang nucleosynthesis, it's really very simple from a nuclear physics and neutrino physics perspective. Again, the neutron-to-proton ratio is just set by the competition between these charge current capture reactions. Okay? They set the neutron-to-proton ratio. In the Big Bang, the nu E's and nu E bars have about the same energy and number densities. And so the neutrons are a little bit heavier than protons. So the net result is as the universe expands and cools, most of the baryon number will reside in the lighter particle, in the protons. The nuclear physics is really very simple. The entropy per baryon in the early universe is large on a nuclear physics scale. You have to be careful how you say that, because if you're working in quantum gravitation, the biggest problem you face is why the entropy of the universe is so low. Okay? But those of us that work on neutrinos, that's a big number, 10 to the 10. That's bigger than 1, and it's bigger than 10. Okay, and so with an entropy that high, one pays a huge penalty for having heavy nuclei around. So there's a competition between disorder and order and binding. And the nucleus that wins that competition is an alpha particle, a helium nucleus. And so what happens is it just scours out all the neutrons and locks them up in alpha particles. And now we're at a low temperature, and so there are Coulomb barriers, and you're left with a sea of protons. The protons have Coulomb barriers, you're done. That's it. That's all Big Bang nucleosynthesis does. One baryon in 100,000 winds up in a deuteron. 1 in a billion or so winds up in a lithium-7 nucleus. Otherwise, that's it. It's over. Material flowing away from a supernova or a binary neutron star merger, where the neutrino energetics is quite similar, the entropy per baryon is 100. You might say, well, 100 is not 10 to the 10. On a nuclear physics scale, it's pretty similar, okay, qualitatively. But unlike the early universe, the nu E bars are more energetic than the nu E's, and that's because the source of the neutrinos is the neutron star, okay? So there's a flip side of that. The opacity that the nu E's have in the neutron star is higher because of that process. So the net result is the nu E bars can drive the material neutron-rich, not proton-rich. But otherwise, the nuclear physics of entropy is the same. And so now you scour out and lock up all the protons in alpha particles, but now you're left with a sea of neutrons. And the neutrons have no Coulomb barriers. So you can get uranium. The neutrons can capture on stuff. A few heavier nuclei like iron form here, very few. You want very few to form, and then the neutrons glom onto those, and in principle you could get uranium out this end, whereas here you're done. Okay? So one important takeaway from what I just showed you is that if you want to make uranium or gold, you need a lot of neutrons. Neutrinos are neutron poison. Nu-E's can capture on neutrons and turn them into protons. And you'll notice that the protons are locked up in these alpha particles, but the neutrons are out here in this electron neutrino breeze blowing through them. And so this is what happens in our models, and this is why neutrino physics is at the heart of ideas about making the heavy elements like uranium. Okay? So what can happen, and I spent a lot of my time over the last decade, or really 2 decades, trying to figure out this problem. The mu and tau neutrinos are even more energetic than the electron neutrinos or the electron antineutrinos, and they're coming out from because they're coming out from deeper in the neutron star, and neutrinos can change their flavors. And so suddenly you can have more energetic Nu-E's, and it makes this problem much worse. Much worse. So what do we know about neutrinos? A lot, actually, compared to what we knew when I started working in this business. We know the mass squared differences from the solar neutrino experiment. Or by mass squared differences, I mean the differences of the squares of the neutrino mass eigenvalues. We know those from laboratory experiments, the neutrino oscillation experiments. So there's a solar neutrino splitting, and there's another splitting, the so-called atmospheric neutrino splitting. The experiments can't distinguish between the order of the neutrino masses this way, called the normal ordering, or this way, called the inverted ordering. We don't call it the abnormal ordering. And my prediction is once we know, if we discover that this is the actual ordering, it would be called the normal ordering, but that's another story. I've labeled the neutrinos here, Nu-1, Nu-2, and Nu-3. These are the energy eigenstates of the neutrinos. These are the mass states of the neutrinos. Those mass states are not, from our experiments, we know they're not coincident with the weak interaction eigenstates, the flavor labels. And so here's roughly the superposition of these flavors that would go with each mass state according to what the experiments give us. Okay? One thing we don't know are the absolute masses. We don't know what the actual masses are. We have limits on them, but we don't know that. Are we going to measure this hierarchy? I think we will. I believe the experimentalists, the long baseline neutrino oscillation experiment, should give us this in short order. They claim 5 years. We'll see. We'll hold them to that. The takeaway from the experiments are the neutrino weak states, the flavor states, are not coincident with the mass states. That means that neutrinos can change their flavors as they move through vacuum or a medium. So calculating how neutrinos change their flavors in medium is a very difficult problem. We thought it was going to be easy because it's easy to figure that out in the sun. It's the MSW effect. It's devilishly hard here. The reason is, as I showed you, a huge amount of energy is in that neutrino field. There are huge numbers of neutrinos. So the neutrinos are moving through a gas of neutrinos. And so it's those neutrino interactions with other neutrinos that determine how the neutrino changes its flavor. In particular, the flavor states of the neutrinos in the gas determine how a neutrino changes its flavor. You see where I'm going with this? So this is a devilishly hard nonlinear problem. It's an exotic quantum many-body problem. And we're talking, my students and I talk to condensed matter physicists who have a very different way of looking at the world than we in particle and nuclear physics. We look at the world as made of particles, and condensed matter physicists know that it's made really of quasi-particles, of normal modes of things. And so it's a very, I'm hoping this will be an illuminating discussion between these groups. We'll see. I showed you what the weakly interacting neutrinos can do. They can bring down these big stars, and they can wreak havoc. And they can actually bring about the transport of energy and entropy and composition, the neutron-to-proton ratio. You could ask, we know the standard model is incomplete. Are there other particles beyond standard model physics that could also play a role in what happens in these big stars? Are there BSM murder weapons as well as the neutrinos? So another takeaway from the experiments is that neutrinos have non-zero rest masses. So that brings up something right away. It begs the question of whether there are so-called sterile neutrino states. have to be a little bit careful with the word sterile. So we might imagine that if there were only two kinds of neutrinos, an active neutrino, an ordinary neutrino that interacts with the weak interaction, and some sterile state that doesn't interact via the weak interaction at all. Maybe it has only gravitation that it interacts with. And there's some unitary transformation between the mass basis for those two states. So nu2 could be a heavy neutrino of some kind. Nu1 is a lighter one. So if the sterile neutrinos mix with active neutrinos in vacuum, like in this, then they're not really sterile.
George?
Yeah.
Is it still possible for one of the neutrinos to have zero mass?
Oh, I think so. Yeah, absolutely. I mean, just from a neutrino oscillation standpoint, I just need a mass squared difference that's not zero. So if I look at this, this is kind of the weak interaction Fermi constant squared, energy squared, is that typical cross-section I showed you that's like 10 to the minus 20 barns at typical energies that we deal with. This sterile neutrino like this would have an even weaker cross-section, like that Fermi constant squared, but now sine squared theta. So for example, sine squared theta for the models we talk about for sterile neutrino contributions to dark matter is about 1 part in 10 to the 10 to 1 part in 10 to the 12. So this would be an interaction that's like 12 orders of magnitude weaker than the weak interaction. This is something we can't really probe in an accelerator experiment very easily at all. And like almost everything in neutrino physics, Bruno Pontecorvo thought of it first. In fact, his first paper suggesting neutrino oscillations was noting that neutrinos could flip from left to right and mix between active and sterile. All kinds of ideas about how you would engineer more weakly interacting sterile states. They could be neutrinos in a dark sector, for example. So this is kind of a very interesting and wide open field. It also begs the question of whether there's a sterile neutrino dark matter contribution. My students and former students and I have been working on this for quite a long time. Basic answer is it's very hard to do. Moreover, there are also maybe cosmologically safe, I have a question mark, dark sector quote-unquote explanations for the so-called neutrino anomalies like the mini-boon anomaly and the results from microboon that constrain it. So here's one, for example, is this great paper by Bertuzzo et al. That kind of runs through all the possible BSM models involving neutrinos in new dark sector physics. Here's a model, for example, with a dark Z and a dark neutrino with a mass of order hundreds of MeV. So this is certainly live. And if we think about BSM neutrino sector examples, we could try to make a dark matter component. And here it's kind of live, as I told the students today, it's kind of live by the sword, die by the sword. The connection with the active neutrinos, even though it's tiny, allows them to be produced in the early universe. They don't come into equilibrium for reasons we can discuss later. But it also allows them to have radiative decays. So here's a picture of a sterile neutrino. Here's the Perseus cluster of galaxies, and let's say the dark matter is made of sterile neutrinos. That sterile neutrino can decay through this loop into a photon and an ordinary active neutrino, a light neutrino. And of course, the dark matter is effectively at rest, so one photon goes that way, the neutrino the other way, and so the photon comes off with, it's a line with half the energy, half the rest mass, effectively, of the sterile state. And we can look for that line, and we don't see it. Or maybe there's some argument about whether we see it or not. So it's just kind of cool that who would have thought that X-ray astronomy gives you the best handle we have on this putative sector of elementary particle physics that we can't probe in a lab. Okay? And you could also ask about CMB constraints, and there are many CMB constraints on other kinds of heavy sterile neutrinos that might not be dark matter. And we can also ask, could they do anything in collapse? Here's a slide from Anna Soliga, who's one of our N3AS postdocs. Here's a collapsed core with neutrinos rattling around inside. Here's an anti-electron neutrino diffusing along, turns into a sterile state. Of course, it zips out and then turns back into an active neutrino. The net result of that would be to renormalize upward the flux of active neutrinos coming from the supernova. That might aid in heating the shock and getting an explosion, for example. We can also constrain it this way, and here are X-ray constraints about the product. the stuff I just talked about on stellar neutrino dark matter, and then Anna's papers argue that those constraints are not very restrictive when it comes to what they can do in collapse. Let me mention this. There may be other things we don't know about neutrinos. So wait a minute, is neutrinos scatter on other neutrinos? We don't have a neutrino collider. One could argue that maybe neutrinos double beta decay is a neutrino collider. But it's a very difficult experiment. Obviously, the cross-sections are really low. But we do have these environments, the early universe and core collapse, where the neutrino number densities are so high that neutrino-neutrino scattering is important. How do I know there isn't some new physics in that channel? Okay? So maybe there's some light mediator, a scalar mediator. So here are ideas, and a lot of these ideas were originally floated as ways to kind of reconcile discordant Hubble parameters, the Kreis et al. Paper, for example, by making neutrinos kind of sticky at the time the photons decouple in the early universe. And we can ask, and we can look at what that does in BBN. The answer is not much at all. And the interactions would be very simple. They need not be flavor conserving. So these interactions could change flavor. Well, we've already seen that if you change the flavor, that could be a big deal. So this is interesting. So what would that physics do in collapse? We're trying to get our heads around it. But again, the collapse is low entropy. And we filled up a degenerate sea of electrons and a degenerate sea of electron neutrinos. So now if I start changing electron neutrinos into something else, mu or tau neutrinos, by interactions like this, that would open up holes that would allow electron capture, but electron capture generates entropy, or it can generate entropy. And if it generate more than 3 units of Boltzmann's constant per baryon, it can melt all the nuclei. Well, remember the whole idea was that the collapse proceeded with an adiabatic index of 4/3. It was almost free fall because we didn't have much Maxwell-Boltzmann pressure from the baryons because they were in great big nuclei. But if I melt the nuclei, that won't be the case. And so we can have weird physics. So if I could draw, this is something I did a long time ago with Ron Maley and Jim Wilson. Here's an arbitrary axis here. XA is a fraction of mass of the baryons that are in heavy nuclei. And you can see in a standard collapse, most everything is in those heavy nuclei, as I told you. And the matter temperature eventually comes up. The heavy nuclei merge in the nuclear matter. The entropy stays kind of low. But if we turn on flavor-changing, strong, essentially more strongly than weak interactions between the neutrinos, then you can see what happens is I melt the nuclei. The entropy goes way up. Moreover, the neutrinos thermalize among themselves to some new temperature, a neutrino temperature, and the neutrino component only feels the ordinary matter through the ordinary weak interaction. And so those kind of heal together at some time. So the collapse looks totally different. Does that happen? Probably not, but it's hard to work out actually exactly what goes on. Let me finish this talk by pointing out some other things that are hints that maybe there's some discomfort in this picture. So the collapse picture I showed you is about stars making neutron stars. Some of them can collapse actually to black holes. There may be evidence for black holes with awkward masses. This is debatable. It's not certainly compelling evidence in my view. But in the future, we might get that. There are the so-called black hole mass gaps where ordinary stellar evolution and collapse lore would suggest it's hard to produce black holes with masses less than about 3 solar masses or something like that. Why? Because this neutron star has got a mass of like 1.5 solar masses and then stuff falls on top of it. So maybe it ends up making a hole with a mass of order 2 or 3 solar masses. But if you found a black hole with a mass less than about 3 solar masses, it would be extremely awkward. Okay? What about, and there's a high mass gap. We'll get to that in a minute. So wait a minute. Is there more murder by dark matter, by BSM physics? So here's the evidence, for example, for the high mass gap from GW 1905-21, which is a merging of the best fit originally. The LIGO best fit was an 86 and a 65 solar mass hole merging to give you a 142 solar mass black hole with an incredible 9 solar masses worth of mass energy radiated as gravitational radiation. Fantastic. There's only one problem. Where did this hole come from? So our model of stellar evolution, which suggests that you can't, with a single star, you can't get a black hole with a mass like that. So for the low mass gap, we could talk about neutron star implosion, or the transmutation of neutron stars into low mass black holes. And there are a number of authors that have looked at this. I'll direct you to recent work by N3AS fellow Anupam Ray, and long ago, before that, Yudai Tsai and Vladimir Tikistov. There could be primordial black holes that are a component of the dark matter. It's difficult for them to be all of the dark matter. We have lots of constraints on that. Here's fraction of dark matter. Here's the mass, something like that. But this is an old idea, probably the oldest idea for dark matter. And again, it's because a horizon volume in the early universe is basically radiation dominated. So it's close to instability. Doesn't take much to shove it over the edge. And you can produce, and there's no shortage of models for producing primordial black holes. What if a neutron star captured one of these primordial black holes? Well, it would consume the neutron star from the inside. Here's a movie by a simulation by David Radice. He doesn't like me to show this movie because it's very crude, very preliminary. He has much better models of this, and this is inaccurate in several ways, but this is a neutron star rotating right at breakup, a millisecond pulsar, or very near breakup. So the material is flying off of it, as you'll see. A black hole will come in here from the left, if we can get it to work. Okay, it's not going to show. We can't, yeah. Anyway, if you could see it, it kind of disassembles the neutron star, turns it into a black hole. This might be a way you could get a black hole with a mass of order a solar mass. Okay. There are many other dark matter models that can do this. With the dark matter, you might look in an environment like the galactic center where the dark matter density is high and the millisecond pulsar density is high, coincidentally, and so that's where you might see dark matter accumulating in the neutron star. You can look at these authors and you can see many ideas about how you could do that. For heavy stars, and again, this goes back to this, and I'll end with this. What about stars in this mass range? So above of order 100 solar masses, here's what happens. The star burns hydrogen to helium stably. It burns helium to carbon and oxygen stably. But when it sort of quasi-statically contracts to heat up to burn the next stage, carbon and oxygen, it suffers what we call the pair instability. So here, again, cup your hands around the material in the star, squeeze it. Here's what happens. These big stars, most of the pressure support is coming from the radiation field, from photons. But the photons aren't all that hot. So that when you push on them, electromagnetic equilibrium shifts some of the photons into electron-positron pairs. That means your pressure support dropped. So you squeeze on this and it doesn't squeeze back. It just converts photons into pairs. That's the pair instability. Gamma 1 will drop much below 4/3. And that brings these guys down. And then so when they start collapsing, it's a race. Can you add nuclear energy by burning carbon and oxygen faster than you go down into this gravitational potential well? Sometimes you can, and you'll get an explosion. Sometimes, usually, you can't, and you just wind up with a big black hole. The mass gap is where you get an explosion, and you don't leave a black hole remnant. So, Can BSM channels ruin pair instability explosions and guarantee collapse to a hole? That would eliminate the mass gap. So there are ideas on how to do that. Katie Fries, who many of you know, who's here, says, yeah, you can have dark matter particle annihilation in these things and add a little energy, and that will kind of skew the physics I just talked about. Sam McDermott and collaborators at Fermilab say, no, actually, you could have extra energy loss channels like those light scalar particles. And that causes the star to burn fuel more quickly. Remember, negative heat capacity. And so that can engineer the collapse also, and no explosion. So the possibilities are myriad here, and just exposing kind of what we don't know about elementary particle physics, the interaction of that with nuclear physics, and the ramifications that could be significant in stellar evolution and collapse. And I'll leave you with this. So one thing we talked a lot about last summer at this INT workshop on dark matter and compact objects and low energy experiments with the idea that there are dark sectors of particle physics. And I talked to Gordy Kane here, who has a very interesting set of models on this. And another expert here is Fred Adams, who's thought a lot about physics related to this kind of thing for multiverse. So are there dark sectors that mimic the standard model in some interesting way? Particles have different masses, different couplings, et cetera, et cetera. But are there ways that you could clump dark matter? One of the particles in that dark sector, one or more of the particles is the dark matter. Can it clump the way ordinary baryons in the standard model do by radiating? So that maybe the dark matter distributions are lumpy, and maybe they form compact dark objects. So can they get into the Earth? Can they get into stars? So I'll just leave you with that.
Thank you, George. Fascinating talk. Let me ask some questions from the audience. Yeah, Tim.
Hi, thank you. So I just I'm just curious about primordial particles, I guess, and this acid, something, but I wonder if in any way they affect nucleosynthesis.
Well, if I could show you the movie, I don't know if I guess I didn't get it to work in your office either. That was one way we proposed, actually, Alex Kusenko and Volodymyr Takistov and I, that you could make the R process and get away from the neutrino poison. That was the whole point, is that these things are rotating, a millisecond pulsar is rotating very close to breakup anyway, where material is just flying off of it. And that material would be very neutron rich and cold. If you swallow a black hole, it will consume it from the inside, at least for some models of the way strongly interacting matter works at nuclear matter density and beyond. It would just simply quiescently eat the star from the inside, but the star would end up flinging off more material. Moreover, as the star moves through the nuclear matter, there are shock waves that eject some neutron material. You don't produce many neutrinos. You also don't produce much in the way of gravitational radiation. You would get something like an electromagnetic display that would look like a kilonova or something like that. But it might be a way that you could have your cake and eat it too. You could get neutrons that were still manufactured by the weak interaction, right? Because they're in a deep gravitational potential well and there's a very high electron Fermi energy. But you're getting it out, you let it decompress, and it makes a wonderful R process. So that's one effect of nucleosynthesis, okay? As far as Big Bang nucleosynthesis, the answer is no. To zero order. Depends on the size of those holes. And if there's accretion on those holes that's going on at the time of Big Bang nucleosynthesis, that might be a different story. Or if they're very tiny and they're evaporating at the epoch of nucleosynthesis, different story, because then we're adding entropy, maybe adding high energy particles that don't equilibrate on the time scale on which the neutrinos decouple. And so that could be very messy.
Yes, Laura.
Can you go back to the slide where you're talking about the flavors of the neutrinos that are coming out? I'm really sure how they flip.
How they what?
Like
yet. This one.
Yeah. So 2 questions. One, what actually triggers the flavoring less than 2? As we talked about earlier, we know the same cause isn't a complete picture. How would this change if there was, say, a 4th flavor?
Okay, so let's just think about how they change flavors with just the ordinary standard model neutrinos we know. So the flavor states, the weak interaction states, are not the same as the energy eigenstates. So when you study quantum mechanics, you know how to solve all problems in quantum mechanics. Take the state you're given, write it as a superposition of the energy eigenstates for the problem, and then I can get the time evolution, right? Because we know that each energy eigenstate evolves in time like e to the minus I energy times time, right? And so I do the same thing here. In an accelerator, we produce, say, a muon neutrino, project that into the superposition of mass states, of energy states, and then evolve each of them in time according to the different masses. Okay, and so as you see, is that as you go along in time, that the phasing changes, the relative amounts of these change, and so that mu neutrino may now have a non-significant amplitude to be seen and measured as an electron neutrino, let's say, okay? So that's how those ordinary neutrino oscillations work in vacuum. Now let's add a 4th neutrino. We can say, well, 3 neutrinos is just a more complicated version of what I just said for 2. But now add a 4th neutrino, and it's basically the same picture, except that the amplitude is going to be really small, right? Because it's going to go like some, unitary transformation matrix element squared that relates the ordinary neutrinos to the mass states, okay? And then an ordinary electron neutrino might have a tiny, tiny admixture of this heavy mass state. I don't know if that answers your question, but.
Yeah, Fred. So I noticed on your list of stellar masses, you went up to rather enormously large stars, right?
Right.
So another issue which you didn't mention is that you actually have to make them, right?
Oh, I don't care about that.
No. Well, my question is, what could you sort of outline where we are in observational space and sort of seeing things in those vast ranges? What's the sort of latest?
Well, I mean, here's my rationale for this, and I'll just channel Willie Fowler, because when Willie Fowler got asked about this, I noticed the answer he gave. He says, I will not answer that question, okay? So Fred's talking about this line, 10 to the 4 to 10 to the 8. Wait a minute, such a star is completely dominated by photons. The photons support it, and it doesn't even have a main sequence. It'll just collapse as soon as you make it, basically. Really, as soon as it goes to light hydrogen, it'll collapse. The lighter end, it might do it in helium burning. And through the Chandrasekhar Feynman instability. So here's my answer to this question. There are supermassive black holes that exist at high redshift. We don't know where they come from. It's an embarrassment. Now, the astronomers may disagree with me. Fine, they know more than I do. But we have billion solar mass holes only a few 100 million years, 500 million years, let's say, after the Bang. How did you make that? The scenario I outlined here shows you how you might make a solar mass scale black hole. How do you go from solar mass scale, we know that nature makes those. How do we go from those things, or even 10 solar masses that we're getting from LIGO, how do I go from that to a billion solar masses in that time scale? And you're not doing that by binary systems radiating away their energy by gravitational radiation. You're sure not doing it that way. Okay? So it begs the question of whether it's a much easier lift if the seeds for those black holes are bigger. Okay? That's my hand-waving justification for why I'm even considering this. Really, it's just fun. Okay?
Other questions? I can't resist following up on the mass gaps. So there's a lot of speculation out there.
You know so much more about this than I do.
I don't know if you're outside of it at all, really, but there's a lot of speculation about the lower mass gap and the upper mass gap being filled by hierarchical mergers.
Yeah.
In 1908, 14 could well have been neutron stars.
And I'll also say, as an aside, that there's a lot of speculation about those things being primordial. Okay.
effectively like a political.
Anyway, go ahead.
But I just wanted, if you were making some kind of a Bayesian decision on what is more likely, is it more likely in your mind that these are just hierarchical mergers, we're just seeing a whole set of generations of mergers after mergers after mergers, getting us into the large mass gap and also the small mass gap?
Yeah, I mean, I would agree with you. That would probably be the more likely route. But that's also problematic in many ways. Where's the environment that's doing that?
Yeah,
And I showed you GW 190512 or whatever it was. That was, you know, and the fit, when I talk to the LIGO folks, they say the fit's not really very good for this 86 solar mass and 65 solar mass.
so many different ways with so many different
Yeah,
interpretations.
there's even a recent Nature paper that interprets it that says a better fit is actually a hyperbolic orbit. So it wasn't even bound orbit. It was, you know, two black holes in some environment having kind of a head-on, right? So my goodness, I mean, think of that. There's so many black holes and the medium is so dense with that. So maybe you get that in globular clusters where you have two-body gravitational interactions, you know, essentially dynamical friction, dragging these things down to the center. And we know that happens in globular clusters. Globular clusters manufacture binary neutron star systems. So maybe it's something like that. Nevertheless, it's an exotic environment. Maybe it's an environment around an accretion disk around a supermassive hole. I don't know what your thoughts are, but.
I know some people who are very fond of that latter one.
Yeah.
Okay, any other questions?